Hey, this is Horner. We're going to take a look at 2005 AP Physics B, which remember is really a modified B. So this is an AP Physics 1 free response question. Notice this is not Form B, this is just the regular 2005. So we have the vertical position of an elevator as a function of time. Notice that it moves up about 16, somewhere around 14 meters, stays there for a while, and then comes back down. So they want us to figure out from the position versus time graph, what is the velocity versus time? At 0 all the way up to about 8, so from 0 to 8, it looks like we have a pretty constant velocity. So let's figure out what that constant velocity is. We need to say that the velocity is equal to the change in position. So here we're going to say v is equal to change in position over the change in time. Change in position is going to be 12 minus 0, which is 12. And the change in time is going to be 8 minus 0, which is 8. And if you take 12 divided by 8, you get about 1.5. So we're going to start right here, and we know that we have 1.5 meters per second over to 8 seconds, so we're just going to move that on over. So now we have the very first part of our graph. From 8 to 10, we notice we get a sad face here. Remember, sad face means it's decelerating to a point where it looks like there's no slope at all from 10 all the way over to 18. So we're going to go ahead and draw a line here to help show that we have a decreasing velocity, which makes sense because that is an unhappy or a sad face. And then from 10 until 18, we should have no velocity at all. So that's what it looks like. At that point, we've got another unhappy face until 20, but we're not really sure where to go. So let's figure out where we need to go. It looks like it's pretty straight from 20 all the way over to 25 seconds. So from 20 to 25 seconds, we're going to do this again. V is equal to change in position over the change in time. Our change in position will be final position is 0 minus, and then we have 12. So it'd be negative 12 over, and we said that that change in time is about 5 seconds. So it looks like it's the same thing, but this time, you know what I think we need to do is take a look one more time here. We've got, yep, 12 over 0, and this time we've got negative 12 over 5. Notice that's different than positive 12 over 8, so this one, instead of being 1.5, is actually closer to negative 2.5. And so we've got to go from 0 to negative 2.5 in that 2-second time span that it's decelerating. See, there's our sad face. We're going to come down here, put this here, go ahead and do our line going down, and then comes back over. And notice that we should stop at 25 seconds. We don't want our picture to go any further than the 25-second mark. And at that point, we're done. Now, the way that they did points for this was you got 1 point for this line, you got 1 point for this line, and you got 1 point for this line because you had to find the acceleration at those 3 points. Then you also got 1 additional point for making sure that you had the acceleration lines here. Remember, velocity versus time, if it is downward or upward sloping, that means that we have some sort of acceleration. Here there's no acceleration, no acceleration, no acceleration. Instead, we just have a constant velocity. And that is the end of that very first part. Let's go ahead and take a look at the next part. It says calculate the average acceleration for the time period from 8 until 10 seconds. So we are going to do the same thing we kind of did before. We're just going to say acceleration is equal to the change in velocity divided by the change in time. From 8 to 10 seconds, we're going to go from 0. Actually, we're going to start at 1.5 meters per second, and then we're going to go down to 0, and we're going to divide by 2. And we're going to find out that our average acceleration for that time period from the graph we just produced is negative 0.75 meters per second squared. Next part of the problem, you probably get 2 points for that part. So there's 1, and you might even get 3, but typically you're going to see 2. 1 for the equation, 1 for the right numbers filled in, and then the solution. You can't just give the solution, you wouldn't get the second point. On the box below that represents the elevator, draw a vector, okay, to represent the direction of the average acceleration. So we are not drawing force, not force. The acceleration we know is negative, so we're just going to draw an arrow pointing down, and that is our average AVG. So I just put A for acceleration and AVG for average. Now it says, suppose there's a passenger of mass 70 kilograms in the elevator, and the student is asked to describe the apparent weight of a passenger at t is equal to 4 seconds. The student explains that the apparent weight is more than the actual weight of the passenger because the elevator is moving up with a constant velocity. What's correct about the student's argument? Well, the thing that's correct is the elevator. So elevator has a constant velocity. That's true. Now we need to give an example. At 4 seconds, the slope of the position versus time is a straight line with a value here of, and I know it's really sloppy, sorry, of 1.5 meters per second. You could say that, or you could say looking at the velocity versus time graph, it's a straight horizontal line with a value of 1.5. So either way, that is fine. What's incorrect? What's incorrect is the apparent weight is, that they say the weight apparent is more than the actual weight. And that is incorrect. Okay, and it's incorrect because we know that force here, the sum of the forces should be equal to 0 because there is not any acceleration. Since our velocity is constant, then there's not any acceleration. There can't be any net force. If there's no net force, then the apparent weight cannot be more than the actual weight. The apparent weight should be equal to the actual weight, which is mg. So the last thing they want us to do in this one is they want us to figure out what is the apparent weight of the passenger at that time, at that 4-second time. So let's go ahead and figure out the weight at that 4-second time. So we need to draw a free body diagram. So straight down, we know we have mg. Straight down is up, and then straight up is the normal force. And when we talk about apparent weight, remember the normal force is the same thing as the apparent weight. So when you stand on the scale, you're not measuring the real weight, you're just measuring how much force there is pushing you back up so you don't fall through the floor. So here we can say the sum of the forces should be equal to 0 in this direction. So we're just going to look at the y direction. That means that the normal force minus mg is equal to 0. And so therefore, the normal force is equal to mg. And that is also the apparent weight. Let's go ahead and do this then. We're going to say Fn equals mg. So that'd be 70, which is the mass of the passenger times 10. And we end up with 700 newtons. And that is the end of this problem.